All right, good morning. Today we're talking about acceleration. So we're taking speed and velocity kind of to the next level. So let's get into our presentation here. So what I want you to do is think about what is the definition for velocity. Once you've come up with the definition of velocity, you can look it up if you need to. I want you to solve this problem. A zebra was spotted 45 miles north of the zoo and was reported missing 9 hours ago. What is the velocity of this zebra? So figure that out, pause the video, and when you come back, when you click play again, we'll go over the answers to both the definition for velocity as well as this problem. So press pause now, and then continue with the play button when you're ready to go forward. All right, so velocity is the speed of an object in a given direction. So that's a bit of a review. So we're going to be talking about acceleration and how it relates to velocity here shortly. And to solve a velocity problem, we want to take the distance and divide that by the time to give us velocity. We have to remember that we need to include direction with velocity as well. So if we divide 45 miles, which is the distance, by the amount of time, which is 9 hours, we arrive at 5 miles per hour north. So the zebra is moving at a speed of 5 miles per hour, and it's moving in the direction of north, which gives us a velocity. Now, if the zookeepers were trying to find this zebra, and they didn't know that the zebra was traveling north, they would have really a much more difficult time tracking this zebra down. They might go the wrong direction and never see the thing. So that's how we do velocity. You should already know that. That's a review. So we're going to speed things up here. Little joke. Objective 313 is determining acceleration. And how do we do that? We use a formula, of course. But before we get to the formula, let's talk about some of the vocab that I want to make sure you're clear on. And also, you will notice that on your worksheet attached to this assignment, the first 4 blank lines are these definitions. So displacement, that's the straight line between an object start point and its end point. So that's the first blank line. The second one is distance, the length of the actual path, that an object takes. That's the distance. So keep the differences in mind. How fast an object travels, or the change in distance over time, is what we call speed. And when we include a particular direction with that, we have what we call velocity, the change in distance over time in a particular direction. So it's the same as speed, it just adds direction. Okay, it's direction. All right, so acceleration is, as I said, the rate at which velocity changes over time. Now, there are some things to keep in mind. An object is considered to be accelerating if its speed changes or if its direction changes, or both. So if you have a satellite orbiting the Earth, it is always accelerating because it's always changing direction. Its speed may be staying the same, but because its direction is changing, then it's considered to be accelerating. So basically, acceleration is any change in velocity. And remember, velocity includes direction. So any change in velocity, we call that acceleration. Now we give certain specialized terms to things like when the speed is changing in terms of slowing down, we call that deceleration. But it's still a type of acceleration, okay, even though it's slowing down. All right, so here's your first quick challenge. And this is on your worksheet as well. And it says, based on the definition of acceleration, which we just went over, are the following objects accelerating? So 1 is a frog sitting on a lily pad, 2 is a deer running across the street, and 3, a car slowing down, and a bird migrating south at a constant speed. So those are the questions. So take a minute and answer yes or no out here in the margin next to each of those statements. and determine whether these objects are considered to be accelerating or not. In a moment, we'll go over them together. All right, let's go over the first one. A frog sitting on a lily pad. Is that acceleration or not? No. The direction isn't changing, according to what we know, and the speed is not changing either. How about a deer running across the street? Yes, that is considered acceleration. Now that's assuming that either the speed is changing, he's getting faster as he goes across the street. So we're assuming it goes from a standing position to a running position or activity. So that would be yes. All right, let's move on to number 3. A car slowing down, is that acceleration? Of course it is. It's slowing down. So we might call that deceleration, but it's still a type of acceleration because it's a change in the velocity. And lastly, a bird migrating south at a constant speed. That would be no. It's traveling in a straight path southward, and it's maintaining a constant speed according to our statement here. So we would have to assume that the acceleration would be no acceleration. All right, so I mentioned, or this statement mentions, I guess, the term constant speed. So there are some terms that we need to make sure that we're clear on. So let's take a look at those. So constant acceleration is when you are going the same speed but constantly changing direction. So your velocity is changing because the direction is changing. So this would be like that satellite example I gave you a few minutes ago. Positive acceleration is in the same direction as the motion, but it increases in velocity. So it's not changing direction, but it's changing speed. It could be changing direction, but all right. So negative acceleration is when the object's velocity is decreasing. The object is slowing down. So this is what we call deceleration, or you could call it negative acceleration. Okay, the technical term is negative acceleration, but you might use the term deceleration more commonly. So that would be equally appropriate. Okay, so zero acceleration, finally, the last definition here. Zero acceleration is what we experience when an object is traveling at a constant speed in one direction. So the velocity is constant, a constant velocity. Nothing is changing, so zero acceleration. So that might seem a little bit odd when you think about zero acceleration. When we think about zero speed, that means it's not moving. But this can be an object that's moving, but its speed isn't increasing or decreasing, and it's not changing direction. So we call this zero acceleration, meaning that it's not speeding up, it's not slowing down, it's not changing direction, it's staying on course. That's a zero acceleration. So that's has a constant velocity. So, oops, I guess I answered one for you. The quick challenge number 2 asks you to determine if a car travels south at a constant rate of 25 miles per hour for 1 complete hour. Is it during this time, what type of acceleration is it experiencing? Is it a positive acceleration, negative acceleration, zero acceleration, or constant acceleration? So go ahead and pause the video, circle the one that you think is correct on your worksheet, and then when you push play, we'll go over the answer. All right, so if you suggested C, zero acceleration, as being correct, you would be right because the speed doesn't change. We are told it's a constant rate of 25 miles per hour. It's for an hour, and it's moving south. It never tells us that it changes direction. So that would be zero acceleration, even though the object is moving. Nothing changes in terms of the velocity. The second prompt, which was already answered for you, stated a bird flies in a circle at 2 miles per hour. During this time, its acceleration is constant. That may seem strange because the bird's not speeding up and it's not slowing down, but it's moving in a circle, which means it's constantly changing direction, right? Because a circle is not a straight line. It's round, so you have to continually change direction. You keep changing from when you start at the top, you go 180 degrees to the bottom and another 180 degrees back to the top, and that keeps going around. So that is considered constant acceleration because the direction is changing. So you got both those right. Good job on the first one, and I gave you the second one, so I don't know. Good job anyway. All right, next. Let's see what's happening. Oh, there's our spin. Yay for the spin. Okay. So the acceleration equation, what we use to determine acceleration and the rate of acceleration, is we take a, and that equals the final velocity minus the initial velocity, so the difference in velocities, and divide that by time, and that gives us our acceleration. So let's take a look at one, and I believe, yes, this is on your second page of your worksheet. So what does each letter in the equation mean? So we're looking at the equation that we just looked at a moment ago. A equals change in velocity divided by t. So of course A represents the term acceleration. This triangle shape means it's really the delta symbol. If you're looking at the Greek alphabet, it would be the delta symbol. But it means a change in. So what would be the change in velocity, right? Because that's in front of the v. The v, of course, stands for velocity. We should already know that. So delta v equals a change in velocity. And the change in velocity is equal to taking the final velocity and subtracting the initial velocity to find the difference, right? The difference in velocity. And then, of course, t equals time. So that's what each of the letters and symbols mean in our acceleration equation. So how do we use it? Well, let's put it into practice here. We've got problem number 1. This is also on your worksheet, so you can follow along. So Tiaza accelerates her skateboard along a straight path from 0 meters per second to 4 meters per second, and she does this in 2 seconds. So we're asked to find her average acceleration. Well, we know the acceleration formula is change in velocity divided by time. So change in velocity, that part means final velocity minus initial velocity. So we need to take our 4 meters per second from our story problem. That's her final velocity. She started at 0. She ended at 4. So that's the final velocity. And our initial velocity, she started at 0, so it's 0 meters per second. So if we subtract the two, that will give us our final velocity, which is 4 meters per second. All right, so we'll move that down to our delta v, and then we need to plug in our time, or substitute time in for t, which is 2 seconds. So then if we put it all together, we get 4 meters per second divided by 2 seconds. That gives us our result of 2 meters per second. Now, acceleration maintains the same unit as velocity does. So it's going to be meters per second or miles per hour or whatever the units are in the story problem. We use those for our unit for acceleration. Oh crap, this always happens. Okay, so here's our second problem, which is also, again, part of your worksheet. So hopefully you're following along and getting these answers down so you have some examples to use with your homework when you get it. But this problem asks us to find the average acceleration of a northbound subway train that slows down from 12 meters per second to 9.6 meters per second in a time of 0.8 seconds. So again, our formula for acceleration is change in velocity divided by time. And of course, change in velocity necessitates us to take the final velocity and subtract the initial velocity from it. So if we plug in some numbers, our final velocity, the initial velocity was 12 meters per second. The final velocity was 9 meters per second. So we already know it's slowing down. So if we plug this in, we end up with -3. So 9 minus 12 is -3. So our change in velocity is -3. Of course, our time is given to us. It's 0.8 seconds. We just plug that in. And then we plug these into our equation. So -3 divided by 8 equals a -3.75 meters per second. So this shows deceleration. So I don't have meters per second in there, but that should be in there. So let's get our unit in there. Meters per second. Looks like a 5. I know. Oh well, what can we do? So we're showing deceleration by having this negative number out here. So because this is negative, we have deceleration. All right.